Recording has started.
Okay, so let me just set up the Zoom. I will try to work with both. Maybe we don't need to work with both in the future, but for now, let's test it. Let's see the sharing. I think sharing probably works, right? Is that? At least I try to share, but I don't know how do I tell? Oh, okay, good. Yeah, I can tell. Okay, sounds great. Okay, so welcome to the introduction to generative AI. So this is um, basically, yeah, basically this class is like a machine learning class. Somehow it's a follow-up of, I would say, CS446. In the sense, it's a continue on that. And the more CS446, I think, covers like traditional machine learning as well as a little bit neural networks. It doesn't really cover a lot about generative AI. So this one is about going to that. So basically, hopefully you have equivalents of the 446, maybe 441. Yeah, I'm not so sure about 441, but the level of the class probably is not expert level. So hopefully it's a more broader level, but it does involve some coding and so on. So essentially you will be able to understand the main concepts. So that's the idea. But it's not application basically. It's more about machine learning. So we will talk about that more a little bit later. So concerning the, let me go through the slides and probably a little bit on the, yeah. So yeah, so this is me, and so my research interest is machine learning theory and some optimization algorithm, and basically adaptive robustness as well as generative AI. So basically, so this is why I teach this class. My office is a second floor, so you can come. Basically, oh, I think office hour here is wrong. So it should be, let me rewrite. This one, I think, just copy paste from earlier one, but this should be Monday after class. So maybe I will update this. But it's on the syllabus, it has the right information. But it should be Monday 11 to 12 after class. Or if you want by appointment, that's fine. Maybe I'll add that. So this is our teaching assistant, which is here. If you have questions, you can ask him as well. Basically, yeah, he is also working on like diffusion models and RL stuffs. So, and he also has office hour. So if you can call him or by other means. Anyway, so this is a course resource, mostly Canvas. Canvas, I think, already everybody can access Canvas now, right? So it's already I made it accessible yesterday, and probably we will have some great scope. Will later come. The website doesn't really has a lot of information, so we probably focus mostly on Canvas. There are actually multiple sessions, so I was thought, but I just update one session. The other sessions you could contain more generality information. But the Grace Bob basically is for I think for some programming exercise later on, and then we will actually do the assignments and through AutoGrader and so on. So okay. So that's about it. So this course, what it is, it's an introduction to basically generative AI. As I mentioned, right? So this is not particularly on application. It's more about generative AI algorithm and machine learning algorithms. And and the machine learning models. We also do some training and evaluation. So you have to know how the model is trained and how to evaluate and so on, right? But again, it's at a broader level, not at the experts level, I would say. So you have a general background of how these models work, and also their motivations. Mathematical derivations, I don't think we will derive for some more difficult ones, but mostly try to, again, the mathematical motivations, I would say. So you know why they are working that way, and something works. Sometimes you can have intuition why that's so on, and so on. Yeah. And the programming assignments are mostly coding, maybe a little bit of theory, I'm not so entirely sure. But mostly just a few exercises get you to play around with these models. I try to use, one thing about the coding is certainly we need the GPUs. I try to make it small. I think for all the modern courses, this is an issue. Maybe you can use Google Colab and so on. So we don't have GPU resources to provide for the class. So you have to do something. But usually they are small enough such that you're just getting the idea, such that it's doable with the Colab, right? So and then that's probably you could try to work. So unfortunately, you have to have some access of GPUs, which I think the school does have some like Jupyter Notes and so on. Those you have to deal with yourself, but not provided by class. Yeah. Again, the other thing is we will talk a little bit about probably prompt engineering anyway, just very little. But this is not about that. It's not about as a tool to do coding, right? Coding agents, how do you most effectively using that? This definitely probably worth some other courses, but certainly not covered here, right? How do you effectively apply generative AI to create contents or other things, right? So this is not about this kind of applications. This is more about machine learning methods, right? So this is just to clarify and get the general expectation. So yeah, so basically this is about this class. Any questions so far? Yeah, maybe we will go through a little bit about, maybe we'll say a little bit of prerequisite topics, some prerequisites, then we'll go to the canvas a bit, just go over that, have more information. So the topics, there are three parts, essentially. So part one, 7 real lectures, but this is a little bit fast. Actually, part one, I would say it's slightly faster than the other two parts, because that's overlap with CS446. So I will just more consider review. The newer part, maybe just the last few lectures, more on the representation learning, which we will, it's probably also covered, but still, we probably say a little bit more. So yeah, so part one is probably faster in the sense. Part review, part a little bit of new information. So and for each part, there are 3 parts, right? Each part we have 2 homeworks, 1 exams. Exam is just in class. It's basically true, false, or multiple choice questions. It's open notes. Probably mostly cover the concepts in the notes, right? So essentially, yeah. I will give some examples later on. So for these kind of questions. Part 2 will be for large language models. This we have 9 lectures. Just cover the basics of a large language model, the concepts, the architecture, the pre-train. We will talk. I mean, certainly not too much, but a little bit, and then just the standard the post-train techniques and some other considerations. Basically, yeah, large language model. So this one, again, there's 2 homeworks, right? The homeworks are for focus a little bit more on coding. In fact, I don't care if you use GPT or whatever to code that. So probably it's not that hard if you use. I mean, it's just you get play around with that, understand how to interpret results and so on. So part two, you have an in-class exam as well. So it's the same. It's mostly covered the concepts which covered in the notes. Yeah, part three will be more for the image generation, right? So I will talk briefly what the difference of these later in the but basically it's multimodal model image generation. They have different techniques, so that's why we will cover those. Again, there's two coding exercise as well as one in-class exam. So basically, yeah, it's organized as such. Each exam is one part only. Oh, let me see. I think there is someone in the chat. Do we have a forum? That's a good question. Not now, but maybe we should create one. Yeah. So right now I don't have. I will try to make sure. Maybe all the TA can look into that. Yeah. Well, concerning the forum. Yeah. Okay. Or maybe Slack. I don't know. Yeah. Okay. Anyway. Yeah. So let's try to look a little bit. Maybe let's talk a little bit of prerequisite. Let me requisite. Oh, actually, I don't. Yeah, prerequisite. Yeah, I think it's good to have some math background. To be honest, especially the first part is similar to the machine learning. The second part is less math, I would say, the large language model. The third part a little bit more, but I will see how to balance that because third part involve actually more probability if we want to go through that. But I will try to make it hopefully not so heavy, right? Certainly you need to Python because all the homeworks, they depend on that, PyTorch, right? You use the Hugging Face and so on. For the other things, it's just similar to the machine learning, basically. You have to have a basic concept of machine learning. I think I should put that basic concept of machine learning and so on. Okay, so let's try to go a little bit of canvas. Let me see. I just want to quickly go over that in case you have questions about this. Yeah, okay. So, right. So yeah. So basically, this is I think a description. We don't. Yeah, this is the correct office hour. Okay. Yeah, this is the correct one. I will correct the slides, and the teacher information is there. Course material, mostly slides, and some reference papers. We'll put that there once we are teaching about the lectures. So I'll put that there if the lectures require that. Lecture slides, there are some books, but those mostly for the basics, right? The basics, so I will put there. And yeah, grading. So there are two types of gradings. One is for undergraduates with a 3. Graduates could either be 3 and 4. So for the grading, basically, okay, because you have a less work for the 3, so essentially it's a 4. So you have 6 homeworks, right? You can skip 2, or you can do all the 6, but pick the grading is the top 4. So that's grading, which give a little bit of favor to the 3 credits. For the 4 credits, it's just all the homeworks and all the class exam is the same. So this is basically for the grading policy. just say you can do less work if you have 3 credits undergraduate. Yeah, so basically that's about the grading. The topics I probably go a little bit more. I already mentioned that there are 3 parts, right? So for now, this one largely I would say overlaps with 446, maybe a little bit slightly different depending on who is teaching that. Yeah, basically we will quickly talk about the neural net. So we will not go through the standard, the classical machine learning, right? So this is not something we will do in this class, but we will go over the neural nets, quickly setting up the training, these 2. The first one will just quickly setting up the training, you run PyTorch and so on, that's starting. And this one talking a little bit about just the concept. Again, this one probably is covered before, but we just review. And this is CNN, then we will sequence models. Sequence model we are talking here is the before transformer, but just setting all the notations. So these 4 probably would somewhere. And then we will talk a little bit more about the representation learning here. Yeah, so basically they're starting representation, the variation autoencoder and contrast learning. So the specifically 2 topics, which we will describe here. And then then we have just exams. For the large language model, basically we will talk starting from transformer and different architectures and models, and then we will talk a little bit about this pre-training. Maybe we will say a little bit of pre-training. Maybe I will see this one instead of these guys. I will probably talk also a little bit about pre-training. And this one then starting with mixing from pre-training to post-training, instruction tuning, scaling law, and so on. This one may be a little bit about prompt engineering, but that's all. It's more from the academic point of view, not from the utility point of view for the prompts. And then we will talk a little bit about the smaller models. How do you train a smaller, like a LoRa and so on, right? So this is here. Then we talk a little bit about the RL. So that's a huge topic. A lot of interest in this in the large language model. Talk about reasoning, right? Like O1, O series, but now they are merging. So, but essentially, 2-section RL, then talk a little bit about evaluation. So basically, yeah, this is about a large language model. So we cover both training, model, evaluation. So essentially, yeah, so training, right, the model, algorithms, right, and some kind of evaluation, yeah. Then we will move to the third one, which talk about image generation. Image generation is a slightly different model. We'll mention soon in the class. Basically, the image generation you have a more probability model. The text generation is somewhat similar, simpler, but but this one is more complicated. Yeah, and then here is some quick, probably at some level, high level, about some topics about probability modeling and sampling. Then we will talk a little bit about GAN, and the more recent GAN is certainly losing favor, right? But still sometimes can be useful. And then we will talk about the flow matching, which is currently more popular methods. It's related, closely related to diffusion, but this one may be a little bit easier. So I will start with this. It might require notation differential equations, but somehow we will try to look at the algorithm level. So hopefully not too much. That's why I'm saying that this part probably a little bit more advanced in math. Diffusion model, and this is a model. This is basically talking about what model people use for the image. That can be combined with that. And then we will talk a little bit about more about the diffusion model. Yeah, I guess that's all. Yeah, that's essentially what the lectures covers. Any questions? Other things? Comments? Yeah. So by the end of the day, I think you get these are basically the main techniques. There are a lot of more advanced details and so on, right? But at the fundamental level, this is basically the main techniques you would encounter in the current generative AI research or machine learning methods, right? So this covers the basically main stuffs. Yeah. So that's yeah, that's about the content. There might be small changes, but these are basically the contents. The small changes may be, let's see, yeah, because this is a little bit tentative. For example, I may do something like maybe a little bit more or less prompt engineering, depends on this on this or something else, right? Or here maybe I will talk a little bit about pre-training, right? So there could be it's depends on how it goes. But generally, yeah, these are the topics. The grading, let me try to say a little bit about the midterm, I think. Uh, yeah. Yeah. So yeah, so essentially there are three parts, right? There will be an in-class exam for each parts. Basically, either binary or multiple choice. I probably give some more later on, some examples, but it's open notes. But you cannot access the internet, right? You cannot say success internet because nowadays you ask GPT, then that's not allowed. So basically, true false question example, right? So something like that. The basics optimization. This is for the first one, right? It's discontinuous. It's you have infinite gradient and the zero gradient elsewhere. Infinite gradient at one point, 0, 1 loss. So you cannot use gradient descent, right? So basically, this is one example. Like so, the basic concepts, right? You have to understand basic concepts. Multiple choice, yeah, this one, these are, again, it's a similar to standard, this would be the part one, right? Similar standard understanding of neural nets. If you look at that, we'll probably talk about the CNN and so on. This is correct because CNN doesn't max pooling, it's just max pooling. It doesn't have a parameter. These are not convex, right? So sigmoid function commanded over. Yeah, this is not correct because they both can model all the functions, different activation. So you have to have the basic concept, and we double all intermediate of we approximate twice as many trainable parameter. That's not quite true, right? Because it's quadratic, right? So basically, yeah, essentially, things like this. Anyway, so this about the exams, what styles and what it is. Let me go back to the slides. Let me see. Okay, so let me move that to. Yeah, let me move this out. Okay, so let's continue. Just talk a little bit about these three parts. So this covers so essentially the course format and so on. Then we will next keep just covering about this a little bit more information about the three parts. Any questions so far? Yeah.
On the exams?
Maybe 20 to 30 or something around that range. Yeah. Yeah. Okay.
Question like in five, oh no, like 2-3 minutes per question?
I think it's about right. Or because it's a one class, it's usually people will actually be much quicker than that. Yeah, because if you know, I mean, especially some of the questions, some of the questions may be longer. Let me think. What is yeah, but something like that. But typically that's the things. Yeah, you can, but in annual. Yeah, yeah. Okay. Yeah, but start with that. Yeah. So let's move on. Okay. Yeah, machine learning. So this one just quickly mentioned. So we will not talk about the classical machine learning, but this one is how the classical machine learning is set up. Essentially, what it does, you first need to define problem as learning, right? So there are different learning regimes, like classification, regression is the most standard. Everybody should starting to know, right? Binary classification, regression is a real function. And then in the classical setting, you prepare the data. After you prepare the data, you basically put the data in the right form. You also do a lot of data cleaning. This turns out, actually, data turns out to be pretty important. Although this class doesn't talk too much about data, how do you prepare data and how do you do that. Turns out data itself, including data cleaning, right, is in the real world, it's maybe 80% of the time. That's all the jobs. So that's actually pretty important job, except they need a lot of detailed tricks and or detailed engineering. So it's not taught. Our project is much cleaner, so we probably don't need a lot of this. But this one happens a lot in practice. You also put in the machine learning algorithms. Learning the traditional setting, you do the feature engineering. Nowadays, a lot of feature engineering is replaced by neural networks, like representation learning, embedding, and so on. They are trying to not doing feature engineering. But in certain problems, even in some modern applications, important applications, people do still need to do feature engineering. So it's not for all the applications. But this one is less so, at least in the current in the modern world than before. So part of feature engineering is already replaced by representation learning. So that's why we talk about representation learning in the first part. Machine learning model and algorithms, right? So machine learning model algorithm is essentially what typically people talk about in a machine learning class, and including this class, right? So we will focus more about the models, algorithms, right? Model algorithms, they may contain training, but they also contain like training objectives. Why you want to train a certain way, right? Why you set up certain objectives. So the problem formulation. So like diffusion model, what is the objective, right? Autoregressive model, LLMs, what is objective, also reflect those. So those are more in the probability thinking. Then finally, it's model inference. Essentially, you train a model, you apply that to a new data, right? So this setting is kind of related to part one, which we will review this machine learning models and procedures. Mostly we were looking at the supervised and unsupervised learning. But the unsupervised, the focus, we are not going to teach clustering again, but we will more focus on the representation learning, unsupervised representation learning, which is something we are trying to work with. Okay. For supervised learning, you have you basically train example. You train a model that predicts unknown information from known. You have labels. You have some learning algorithm. And once you labels a learning algorithm, the product of that is a model. It's basically model usually is a function. It's a function which maps new examples to its labels. So this is a standard supervised learning setting. The supervised learning mostly we associate with both classification and regression. In fact, the supervised learning, sometimes it will go a little bit beyond that. In the traditional machine learning setting, it's not before neural nets. People look at so-called complex prediction, right? Complex prediction or structured prediction, which label can be a sequence, for example. This one involves with like sequence prediction, which coincide with something like neural networks or coincide with something like transformer or large language model and so on. But for the most basic ones, they are just simple regression, simple classification, which we will do. Example of a classification is image classification. Basically, you assign a label to an image. This is a very classical example. When deep learning comes, this is ImageNet. When deep learning actually is starting to get popular, certainly is the first example. It works on was on the ImageNet, was on image classification. That one essentially effective label on image is actually important progress. Although nowadays people move to be much for more complex tasks, but this one is still the basics fundamental, and also a lot of architecture advance actually coming from this kind of research. So you design new architecture, some new training tricks, training algorithms, and so on. Also so set up from here. This one is probably around starting to get into deep learning, maybe 13 years ago, right? 2012, I think, around. That one you have a first AlexNet, which was working on with this image. Then there are a lot of development in the following years after that. Another one example is regression, right? Regression is predicting real numbers instead of predicting the categorical, the labels. I mean, stock prediction, right? Or the price prediction, whatever the prediction problems, usually they involve a lot of involves a lot of real numbers. Again, typically, what are these kind of supervised learning in the traditional machine learning, right? So this is the terminology we will also use, is that you have an input, usually it's prepared, whatever is image, it's something text, it's represented as a vector. The vector is, in the traditional setting, is a d-dimensional space. In the modern setting, it could be more diverse, whatever the representation, but eventually it may convert it into some representation, so-called, in the d-dimensional space. But basically, it's a vector. So or you either the vector is the original data or it's actually learned data, like the representation learning we will talk about, learn these kind of vectors. Output for the regression, it's just a real number. It's continuous value. For classification, it's a binary or it's a multiple categories. And you have a training data, right? Training data is X, Y, you have N of that training data. You are learning algorithm effectively does the following. So the learning algorithm in abstraction, it takes your training data, takes a sequence of data, N data, and it return a model, right? The model is actually a function. It's basically the function which takes future x, where is a vector. It takes a future vector and returns some output labels, for example, label. So basically, this is a kind of model. And these models, there are a lot of examples of these kind of models, right? So in the traditional learning, we have linear models, which is most basic. We have something like a support vector machine, decision tree, boosting, and so on. So those are all models, which we tend not to cover in this class, but we are more looking at the neural networks. Neural networks, again, it's a model. It takes input, going to output. So basically this is the setting. For the unsupervised learning, the unsupervised learning, actually, it's different, right? There's no label. So what do you learn, right? So it's I try to discover some patterns. So that's the idea. Try to discover the relationship in data without using any explicit label. So basically, there are many different methods or different directions in the unsupervised learning. Certainly clustering is a classical example, your clustering analysis, and it's also very useful. Sometimes clustering can be used to generate the features. Features then goes to the supervised learning algorithm. For you just looking at X, you do a cluster of X, then you create some features, then you create, right? But more example is related to the representation learning, which we will talk in the first part, the last few, maybe last 3 lectures, right? So will be the representation learning. It's closely related to dimension reduction. Dimension reduction is kind of a representation learning. Classical example is PCA, principal component analysis, but more recent is autoencoder, variational autoencoder, right? Contrast learning, and so on. These are the things we will talk about. Smarter dimensionality reduction. And how to do that? These are the, but there are also other things. Other things we will not cover. Anomaly detection is important in real-world application. How do you find your data is something wrong? And there are techniques to do that using unsupervised learning. And there are associated learning, and there are some others. A topic model is like clustering. Actually, it's closely related to clustering, also related to the representation learning. But for the modern ways, instead of using clustering to do representation learning, usually we use some sort of a dimension reduction, but more general, yeah.
Are encoders do dimension reduction in like transformers and models?
Encoder?
Yeah.
Encoder, yes, encoder will give you representation. Those are you mean for the transformer? Essentially, for the transformer, the last layer. Typically, you can encode the whole sentence using the last, either the average of the last layers embedding or use the final embedding. That's very standard. And that is used, yeah. But yeah, when we talk, but those also can be considered representation learning. But when we talk about representation more and more in the unsupervised, we will, yeah. It's, this one we will probably discuss that in the second part, right? When we especially talking about RL and so on, yeah. But yeah, but they become a vector. Essentially, after representation learning, usually they become a vector. Yeah.
For this.
Sure. Yeah.
In this, like, why are you writing like model as like an algorithm over data? Because like it looks like the same form as the one though, like y hat equals m of x, because m at the end of the day is a function, right? And x comes from the data set, or
right,
is the data set.
Right.
So why are you writing on top of that like m equals like an algorithm over a data set?
Because you have a data set, you have algorithm, learning algorithm, it gives you a model. Okay. So it's a function of the data set. That function is your learning algorithm. Yeah. Your learning algorithm takes data set, return a model. Right. So it's a procedure. Let's say your procedure, yeah. The procedure input is a data set, output is a model. Yeah.
I'm saying that because like the
right.
model changes over time with the data set, that it needs an algorithm to like update itself.
Yeah.
Okay.
But, yeah. Yeah, this is unsupervised learning. Clustering is the example which we can take, right, as clustering. However, we actually can do a little bit more. I mean, clustering is I'm just giving as an example of people all have seen that with a machine learning class. But clustering is not something we are looking at. This one can be considered as a representation learning. Basically, it's a representation about this data. You have a lot of data. You only have 3 components of your data, read, and so you have 3 index. Then becomes representation learning, right? But what we are actually interested in more general. So this one will be, I think, the last 3 lectures of the first part will be on this topic. Representation using the unsupervised learning to do representation learning. So the idea is you are learning a low-dimensional representation of data, right? That captures the important structure without using labels. But you know, this representation can be used for downstream tasks. For example, supervised tasks in the future when you want to use that. So this is generally the way we are framing that with. The general formulation is the following. So you have input data. This is a generative formulation. It's maybe a high-dimensional data, some other form, whatever it is. And let's say it's a D-dimension, right? So representation is sometimes called the embedding. Is you map this data into a k-dimensional space. The k is typically much smaller. So from this unlabeled data. So this is and then you can use this to do whatever things you want after this. There are different ways to utilize. You can use that for example, for retrieval, right? So you can use the retrieval if the similarity usually in this embedded space item become more similar. The similarity of X becomes like, for example, dot product in your vector space. Then you can use that for retrieval. Or you can use that for the supervised learning as a feature to do the supervised learning, and so on. So this is a very general. This is actually quite, I would say, quite essential or quite important conceptually in the sense of that basically what the neural networks are doing. They try to form better and better representations. And in the end, you have a simple representation such that it already clearly tell what you want, right? For example, if a cat and a dog is what you're targeting, you hope the representation such that cat all be together, dog all be together, but between the cat and the dog, they are far apart. So you have to certain structures like that. Eventually, it will emerge. So from this kind of representation, clustering itself could be doing that. I mean, the clustering assignments could be, but more about that it will be dimensionality reduction. So this is what we actually try to look. There are a few representation methods we will discuss, but we will cover more like a nonlinear generalization of PCA. It's basically autoencoder and variation autoencoder. And then we will also talk about a little bit different ways to handle that. That covers a certain range of contrast learning. So that's also unsupervised representation learning, but using a slightly different idea. So yeah, so essentially, this is important. This one turns out the learned representation will be useful for many other tasks, even though you are doing some unsupervised learning. So you could also do using supervised learning to do representation learning. So you just learn, for example, the classical example will be you learn a neural network which perform well on ImageNet classification, right? Usually this neural net, like a convolution neural net, it will go back to the top layer. The top layer will be a vector. Before doing classification, that can be your representation of your image. So that's also possible, using the supervised learning to do representation. But mostly people more interested in the unsupervised learning because there are many more examples of unsupervised learning. Supervised data are costly, expensive, right? So you want to have unsupervised data so that they are actually many, many more data. And the amount of data which gives you a more powerful model because you are actually yeah, you just have more data. So essentially, yeah. So this is quite useful and what we will cover in the first part. As probably, I think this probably up here, but this one probably talking more than the standard machine learning class in this class. Now then we will move to the generative models, which is essentially the majority of this class, right? So part 2 and part 3. Both for generative models can be both for think about the supervised or unsupervised, depending on the different views you view that. I was just doing a simple view for this. Basically, okay, a generative model is a linear distribution of data. In the unsupervised learning, usually it's called unconditional. Then you have no prompts, you just generate data like image, right? So that's an example. That resembles original data. For example, you train an image model, generation model, you just generate like a natural image. Prompt means you are telling more specific. This is where more like inputs are, label, you can think. And given this label, you again generate image, but you say, oh, generate instead of a generic image, I will generate a cat image. So if a prompt is cat, and then you have a generative model. Basically, this is a kind of model. Essentially, what the difference of this versus before? I will talk a little bit more details. How it's related to the traditional and what's the difference and so on, right? So, but there are some difference, which especially in the continuous setting. There are examples which VAE actually is more now based on representation learning, but this traditionally is also considered as a generation model. But now I don't think people use that for generation, more for representation. Variation autoencoder, which we'll cover actually in the part 1, not part 2. GANs will be examples, right? Diffusion models are examples. These are for image generation. Autoregressive models, which are more can be for image, but it can also be for like LLMs, right? So autoregressive model is mainly for LLMs. So what are difference about these, right? So we will try to talk a little bit about that. So For the unconditional generation, right? Just say generating something like image, right? You observe a lot of images. Why? Can we generate other instances that are similar to these observations, right? So this is a question. Or you can generate something like a text, like a story, right? Just a free generation without any prompts, right? Can you generate that? So this is about just to say you just say generate content in certain domains, say news articles and so on. So these are the basically part 2 and part 3, and part 2 about the text, part 3 about the image. What are probably more interested, more similar to the supervised setting, will be you have prompts. When you have a prompt, essentially you have an X. X is your prompt, and Y is associated with X, is something you want to generate. Yeah, basically the way of I would say generative model versus traditional machine learning. Traditional machine learning is more focusing on the prediction, right? This one is more focusing on generation. Prediction, you just predict which one you pick the largest. Generation, you really need the sampling. And for the part 2, we are looking at the text, right? So for example, it's a question or it's an answer. We all know that because everybody probably familiar with GPT. You just ask, then they will give you an answer. Part 3 will be the image, right? So you say, okay, I want to generate an image, for example, beside the mountain or whatever, right? So, and then there's a village, there are some people around and so on. You just give the description, then you generate the corresponding image. So this is essentially the application. And these two actually has different models. And in our class, we are more interested in the underlying models with this kind of, for this kind of methods, right? So basically, yeah, what is a model, right? So if we start with a model, the classical statistical approach is still relevant for this kind of a generation. Is we want to model a distribution of y. This is for unconditional, but we can make it conditional as well. Basically, there is a model parameter theta, which is trained from observation data, and then you sample y from probability of y. So essentially, you first do a probability. You also do proper model. You train the model parameter from observation, your training data, and then you actually sample from this y given theta. And what is the approach, right? So this one is slightly different than the current way of generative model in terms of images are generated, continuous variables. But for the discrete tokens, like LLMs, it's using this pretty much this approach. So we will talk a little bit about the, quickly talk about this, and then we will go over more. So, but this one is more about this one we actually will cover in the first part, but especially the second part. But the second part we are not per se talking about the sequence model. We are more talking about more specific to LLMs itself, right? So instead of sequence model. Sequence model is more generic. It exists long before LLMs. And the idea of sequence models, you have discrete tokens of a certain length. You have L is your, say, length, number of tokens you want to generate. Then you basically generate it one by one. So that is a sequence. We can also call that autoregressive model, which is a pretty standard terminology nowadays. Autoregressive model, basically you just generate one token at a time, conditioned on everything else you already generated before. So basically this is a model, and these are the generated tokens. Why? Theta is your model parameter. It's basically your model. Say your parameter in your transformer and so on. And Representation, of course, the most powerful would be like GPT type of models, large language models, which turns out to be important, which we will cover more. This we will actually, starting, if you look at the syllabus, this one we will talk about in the first, the generic sequence model. For the second part, it uses the sequence model, use this autoregressive, but we cover additional topics, right? Not about the sequence modeling. But the idea is that GBT does use this particular model. Sampling discrete is easy. You just you have marginal, you just sample according to the probability of a token you predicted, right? So in this case, sample is easy, the point, and then you can do the sampling. LLM, I just quickly mentioned because so it's surprising in some sense. The sequence model can do so much as LLM does, which was unthinkable a few years ago before GPT comes up. They don't imagine sequence model can be actually this powerful, but apparently it is through this demonstrated by the large language models. And people talk about, there could be something. This is a lot with AGI, right? So at least it's a one approach. There are arguments about this. So essentially, I think you probably hear the news. There's arguments about what the AGI, whether LM is sufficient, right? But there are some capabilities you can say about this kind of AGI models. You definitely want that human-like reasoning, planning, right? Solving problems and so on. You can communicate complex ideas. This is more about communication, collaboration among either different LLMs or LLM with people or people with people, right? So you can think, right? So these are the things which matter, both from language perspective. And you also want to learn adaptively, learning from experience, and so on. For example, basically, if you're doing something today, right, if you say you're doing something dangerous, you hurt yourself, you will be avoiding doing that next time, right? And you can continuously learn. If you read a book, you remember that. And you also need to, if we want to say, okay, beyond the virtual world, right? You could do a lot of things with virtual world already, but let's say beyond the virtual world, then you also need to do the physical world, right? So for LLMs, the question is, what are these one which can be solved or potential, or what are not solved by this? Yeah, you can.
I think it does like the third one really well, learning adaptively. Like it is able to like if you tell, oh, you've done this wrong, like okay, let me try and correct. It does that really
Okay.
well. First one, it does somewhat well. It depends. Getting better, I think.
Yeah.
But earlier it was not good, but now it's getting better at that. Second one, like communicating, I think it does really well.
Right.
Comprehending, I'm not like it's like using LLMs for learning is really good, like in that way. So in many like so it communicates really well.
Yeah. Yeah.
Fourth one, I don't know.
First, yeah. So maybe I'll comment here. Yeah, I mean that's good. The thing about first one, I think it's mostly moving towards. So that's differentiate LLM from the previous one. That definitely show the ability to answer questions, which is the second one for the NLP, right? NLP is considered very hard, but after LLM comes up, it becomes much easier. A lot of things are addressed. First one, because there are reasoning models and so on, they are solving different problems gradually at the different levels, which is also pretty good. Yeah, I think it's also improving. Essentially, I think LLM considered mostly target these two. For third one, depends on how do you view that. What typically view people when they talking about this, right? They just say, okay, let's say I train. Usually, people probably don't know that, and this probably in all the news or whatever, right? There's a pre-training stage of LLM, right? Usually, there are two stages. Our class mostly cover the post-training. There are a few things. After pre-training, then post-training. Pre-training basically give very generic. You train on the internet data, huge amount of data. Post-training is refine that so that they will talk more. You filter out some garbage, more specifically talking about what human likes, sometimes called we're giving some reasoning capabilities. Now, when we talk about continuous learning, right, basically say the following. When you get more and more data, for internet evolves, right? Let's say I have more news, I have something. Instead of doing pre-training over and over again, I will just adding this information to the pre-trained model. Can it do that? Actually, if you think about that, actually the current machine learning doesn't allow this to be done effectively. It actually doesn't work well. So no one has the continuous learning from experience. Like human can do that much better, right? But none of the model, including LLM, cannot do that because you have to start from scratch pre-training. If you don't do that, what happens practically is you will tend to forget about the knowledge you learned before much quickly. Once you're starting to get new knowledge, you learn the new information. Much more forgetting than human would be. Human will forget as well, but when you learn new knowledge, usually they put orthogonal. They try not to just influence the older knowledge as much. So it's actually very interesting. And then this is a lot of current research trying to resolve that. It's known that this is something which isn't easily to do. And this is certainly not of this class, because this is more on the research side. And no one yet figure out, but there are some progress towards this, I would say. But then, LLM certainly doesn't able to that. They could actually give you some tasks, descriptions doing more, but most limited in already learned. You will not be able to learn more. Basically, it will not improve itself. It just can solve some newer problems. So that's what it can do, yeah. But it cannot really learn from these new examples for example, to be a better GPT, right? Yeah, yeah.
Third one, like, why doesn't post training allow it to do that?
Post-training, it's just the two stage, and you have to be very careful not to forget too much about it. It will tend to forget a little bit. Whatever your post-training is doing tends to be a little bit of forgetting about certain things you could do before. But yeah, but it will target to much more useful things, give much more useful, yeah. Because the internet is not on target. It's a lot of garbage, a lot of things, yeah. So basically, yeah. That's what you do. And it will extract certain capabilities like reasoning as well. Yeah. So it's a trade-off. It's a trade-off. For the physical world, people are working on that, but LLM doesn't directly solve that. These are actually like some well-known figures like Yang LeCun, which very vocally says, right, you need this. But anyway, so. But this again, this is very impressive. You could get these two even. I think it's hugely impressive. It's a few years considered impossible. Let's say it this way. Yeah. And I think I will just quickly go. I think I will skip these two. But maybe I'll quickly go. Yeah. Basically, the common sense knowledge. Something are considered now, you already see that maybe for the newer generation, they don't even know things before the LLMs, then they don't think that's hard, but actually it was hard, very hard for the natural language. It's considered much harder than image, but somehow now it's much better, yeah. Common sense knowledge, people try that. Even in the virtual world, you never see any physical things, right? it's impressive that it actually can reason according to physical knowledge. I don't know how it works, but somehow it just does have a certain common sense. Sometimes make errors, but human also make errors. So for these sites that does that. Turns out it can also use tools. The tools can give some physical ability. Multimodal LLMs, like we will talk about that, it's a little bit more limited, but essentially it's able to do that. And this one also is progress. So maybe in the future, I would say maybe a few years, with multimodal, much better multimodal integration, can indeed do the physical understanding. So that's not unthinkable. It's definitely something which is possible. But it's definitely, even if doing that, this is something I can see is possible within current technology by using multimodal, which we'll have one lecture cover multimodal, the simple versions, but the more complex versions. I think it's still a little bit harder to say it can do the continuous learning. That is harder. That needs a much more change. Yeah, currently the training doesn't work. Basically, the way if you're starting getting the data, you just continue train. It just doesn't work. Yeah. And there are some issues. Continuous learning definitely is an issue. This one may be solvable. Something can be solved. This one, there are a lot of people actually working on this. This one is something needed, short-term or longer-term memory than this one. But this one, people make quite a bit of progress. Yeah, and there are other issues, efficiency issue and so on. So this is about the LLMs. Now let's move on to the what we want to do with the third part. Right. Second part, we will just brief talk about the LLM related issues. Again, second part, we will not, because there are not too much talk about the probability modeling, sequence model. Right. I already give that slide. We'll have one lecture in part one talk about that. So we will talk second part talk more LLM specific things for the sequence model. But for the third part, you have to go back to talk about how do you do that, right? So there's no standard ways of do that. This one shifts more from the traditional statistics in the way how this is done for the continuous observations. How do you generate those instead of discrete tokens? This will be the topic, actually, part 3. Yeah, so I'll make the part 3. A popular mode method. This is actually the current ways doing that. Is how do you sample, right? You first sample from Gaussian noise, right? Diffusion models, they starting with noise, but all other models are all the same. And then you generator. This is called generator. You map Z to any continuous variable. This turns out to be pretty effective. There are different ways of how these G are learned. This is certainly the thing. So the idea is, can I map Gaussian using a G to arbitrary distribution? More or less, it's a yes, right? So you could map a Gaussian to an arbitrary distribution. But how do you want to learn this G? It will be all these generative model from machine learning perspective. They will tell you, you do this, you do that, then you'll be learn G, right? This is one example about, first I will just say, well, this is one example about this one-dimensional, a simple example about this G, right? Left-hand side is a Gaussian. Basically, this is where you can sample from. You know how to sample from. Right-hand side is maybe your target distribution. In this case, I specifically make it multimodal, make the 2 different shapes, right? And then can you sample from this one passing a G to this one? Yeah, this is one example of this function. This function makes such that they will split this Gaussian into 2 parts. But you can do whatever you want. Essentially, you can do more complex things, make it actually kind of to other shapes you want. And now, left is basically the randomization where random comes in, sample in. This one is a deterministic function, right? A deterministic function take a random input, map to a random output, basically, right? And this determinant function Z is what you want to learn in the modern generative model. both in GAN, in diffusion model, in other things, right? So basically, this is key ideas is focusing on learn this so-called generator as opposed to sampling, using generator to solve the sampling problem. So yeah, so basically this is what it looks like. You could also do multi-stage generation instead of one such G. Turns out you could do multiple Gs, G1, G2, G3. You move this one a little bit away from the Gaussian and a little bit away each step until you hit this target. This is how the actually diffusion model is doing. They are not using one big G. They are using many small steps. Each time doing a little bit of denoising. You're starting with a noise, then you denoise, and this is example. Oh, so I don't know why. Oh, I think this one is messed up. This one, this doesn't compile well for whatever reason. I think I should have this showed up. Basically, I just each time denoise. Maybe I think I probably have another slide. This slide is not the right one. Let me try to get the other one. Let me get to. I think I probably use the. Hold on. Let me. Yeah. Okay, this is the right slide. So yeah, sequence of generators, right? So you first this is noise. You are just move using G to move a little bit about this one, map a little bit, map a little bit, map a little bit, and map a little bit, and essentially you get the kind of image. So basically, yeah, this is like what it looks like. So you can have multiple Gs. And why you want to do that, and the stability, a lot of reasons, and we will cover that. So basically, in the I think in the part 3 we will have a few lectures on this, maybe 4 actually, talking about this kind of models. One is GAN. GAN is the earlier model. How do we learn generator? It's popularized this generator concepts, but that's a little bit unstable. Then diffusion model comes up later on, which flow matching will, so we will talk about flow matching. We will talk also diffusion model and so on, probably also the formulations about the diffusion. So yeah, this is what it would be. But anyway, so in summary, so I think this class basically hopefully gets you the idea about this class. Part 1, ML foundations review. We have both supervised learning, which all the standard neural network models, CNN and LSTM, whatever, sequence models and fully connected neural nets, right? And classification regression, right? So this is the standard. And for the unsupervised learning, we will focus on representation learning. So this is part 1. This one may be a little bit more beyond the standard class. Part 2 is a generated model. Basically, for the generated model, as we mentioned, it's a sample from the data distribution. So that's the key. You sample from data distribution, probably based on prompts, both image and text based on prompts. Adding prompt doesn't make too much difference. Basically, not adding prompt is like unsupervised learning. You are learning to generate. Adding prompts is like supervised learning. You have a prompts, right? So you have inputs. But essentially, the modeling doesn't matter too much because prompts really coming from here already, covered from the modeling perspective. Just adding that as condition. Yeah, conditional model and non-conditional. So part of 2 is auto-regressive model. What we are talking are more not about this probability model. Probability model itself is rather easy, but we are trying to actually try to think about how the general process, more specific to the LLMs, right? How that works and related to this part 2, and as a general knowledge about mostly focusing on the models as well as post-training. Part 3 is for the continuous distribution. Again, it's a more general education, mostly on the image using a generator and or sequence of generators, like a diffusion model to map a random noise to an image, right? So basically, it's a but it doesn't have to be an image. It's more about the continuous distribution. So that's the difference of this one, discrete tokens. This is a continuous distribution. Okay. Yeah, that's all. So we will next time we will talk about the neural nets as a review. Okay, next. Yes, yes.
I'm currently not in this class yet, but I want to be auditing the class.
Sure, you can. Yeah.
So to get access to the course material, how do I do that?
You